Hello everyone. In the previous lecture, we have introduced the calculation of settlement of ground soil. This settlement is commonly called the final settlement. Sometimes, in engineering design, we need to pre-estimate not only the magnitude of a foundation, but also the length of time required for achieving a certain settlement. So, this section, we will talk about time rate of consolidation. In this section, there are two problems need to be resolved. One is calculate the primary consolidation settlement at any time t. The other is calculate the time t needed to reach certain value of primary consolidation settlement. As mentioned in the first section of this chapter, the mechanics of the one-dimensional consolidation process can be represented by a simple model. From this model, we can draw the following conclusions. Settlement is a direct result of a decrease in volume. Immediately after loading, all the applied load is transferred to the pore water, so that the pore pressure increases by the same value as the applied load. The excess pore water dissipates with time due to permeability, as water drains out of the soil. For coarse-grained soils, the process is instantaneous, and for fine-grained soils, this process occurs over a long time. During consolidation, as more water squeezes out of the soil, the applied load will gradually transfer to the soil skeleton. At the end of consolidation, all the applied load will be carried out by the soil skeleton. Based on these conclusions, we can consider how much will the fine-grained soil settle and how long will it take to finish. Currently, the relationships between the foundation settlement and the time are established based on the Tazagi's one-dimensional consolidation theory for saturated soils. The theory considers the rate at which water is squeezed out of an element of soil. It can be used to determine the rate of volume change of the soil with time, settlement at the surface of the soil with time, and the dissipation of pore water pressure with time. The mathematical derivations are based on the following 6 assumptions. The soil is saturated, isotropic, and homogeneous. Soil particles and water are incompressible. Darcy's law is valid. Coefficient of permeability K, coefficient of compression alpha, and the coefficient of volume compressibility MV remain constant, whichever usually decrease during consolidation. Flow only occurs vertically. The load is applied instantaneously and over the whole of the soil layer. Total stress is constant. Let's consider a layer of clay with thickness 2 times HDR. HDR is the length of maximum drainage path. The clay layer is located between 2 highly permeable sand layers. If the clay layer is subjected to an increased pressure of delta sigma, the pore water pressure at any point A in the clay layer will increase. For one-dimensional consolidation, water will be squeezed out in the vertical direction toward the sand layer. This figure shows the flow of water through an element at point A. For the soil element having dimensions dx, dy, and dz, the rate of volume change is equal to the difference between rate of outflow of water and the rate of inflow of water. So, the rate of volume change can be expressed in equation 1 or form 2. The flow velocity through the element is given by Darcy's law as the following equation 3, where A is the hydraulic gradient. Since any change in total head H is due only to a change in pore water pressure, the flow velocity can be expressed in x pore water pressure, caused by the increase of stress. Submitting the expression of flow velocity, equation 4, to the rate of volume change, equation 2, equation 5 can be obtained. Moreover, the rate of volume change can be expressed in terms of coefficient of volume compressibility MV in equation 6. When x pore water pressure decreases with expulsion of water, the total stress increment is gradually transferred to the soil skeleton. Increased effective stress. According to the effective stress principle, the rate of volume change can be expressed as form 7. Combining equation 5 and equation 7, the differential equation 8 of consolidation can be gotten. In the equation 8, for one-dimensional consolidation, Cv is defined as the coefficient of consolidation, and the suitable unit is square centimeter per second or square meter per year. Since coefficient of permeability K and the coefficient of compression alpha assumed constant, Cv is constant during consolidation. Moreover, Cv can be expressed in terms of coefficient of volume compressibility Mv or constrained compression modulus Es. The basic differential equation can be solved with the boundary and initial conditions. The general solution for the export water pressure at depth z after time t is given by equation 9. M is all the positive integer. Tv is a dimensionless number called the time factor. The time factor Tv can be expressed in equation 10. HDR is called drainage path, which is the longest vertical path that water will take to reach the drainage surface. If free drainage takes place on its upper and lower surface, namely two-way drainage, the layer is described as an open layer, and the length of the drainage path is equal to half the thickness of the layer. If free drainage can only take place at one boundary surface, namely one-way drainage, the layer is called half-closed layer, and the length of drainage path equals the thickness of the layer. Because consolidation process by the dissipation of export water pressure, the degree of consolidation at a distance z and at a time t can be defined as equation 11. U0 is the initial export water pressure. UZT is the export water pressure at time t during the consolidation process. In practical problems, the average degree of consolidation for the entire depth of the clay layer is applied widely. The average degree of consolidation at any time t can be written as equation 12, where St is the settlement at time t, Sf is the final settlement when the export water pressure becomes 0 throughout the thickness. Therefore, the consolidation settlement St at time t is given by the product of the average degree of consolidation capital Ut and the final settlement Sf. Combining the following equation 9 and equation 11, the degree of consolidation at any depth z can be obtained. The variation of degree of consolidation capital Uz with the 9-dimensional time factor Tv is represented in this figure. Substituting the general solution Uzt for the export water pressure at depth z after time t into the average degree of consolidation capital Ut, it can be seen that the average degree of consolidation is a single value function of the time factor Tv. According to the equation 14 of average degree of consolidation for double drainage and U0 constant case, the variation in the average degree of consolidation capital U with the 9-dimensionless time factor Tv is given in this figure. The equation of average degree of consolidation can be represented almost exactly by the following empirical equation 15. This figure shows you the relationship between Ut and Tv for different drainage conditions, and U0 is not constant, where the parameter A is the ratio of the consolidation pressure on the previous boundary surface to the consolidation pressure on the imprevious boundary surface. So for the case of one-way drainage, we can read off UT or TV from the chart directly. For the case of two-way drainage, namely open layer, the average degree of consolidation can also be calculated using this figure, but A is equal to 1, and the drainage path H should be half the thickness of the layer. The time factor TV provides a useful expression to estimate the settlement in the field from the results of a laboratory consolidation test. If two layers of the same clay have the same degree of consolidation, then their time factors and the coefficients of consolidation are the same. We can get equation 16. By simplification, the relationship between laboratory and field consolidation can be obtained. In practical engineering, the following two types of problem related to time rate of consolidation should be resolved. One is how to calculate the primary consolidation settlement at any time t with known final settlement SF. For such problem, firstly, the coefficient of consolidation CV can be calculated using the known values. Then, we can get the time factor TV of the soil layer. The corresponding average degree of consolidation UT can be read off from figure. Therefore, ST can be calculated using this equation. The other problem is how to calculate the time t needed to reach certain value of primary consolidation settlement ST with known final settlement SF. For such problem, firstly, the average degree of consolidation capital UT can be determined. Then, the time factor TV of the soil layer can be read off from the figure. Therefore, the length of time t required can be calculated using this equation. Let me summarize. Kazagi's theory of one-dimensional consolidation is introduced. After the load application, the degree of consolidation for a given soil layer at a certain time depends on its coefficient of consolidation CV and also on the length of the minimum drainage path. Thank you for watching.